Hello and welcome to the Raised Beaches podcast. I'm Dr. Evan James Gowan, but you can call me Evan. This is episode 2, and I'm filming it in a very special place, the Kikai Institute for Coral Reef Sciences. So Kikai Jima is an island in southern Japan. It's located in the Ryukyu chain. So the Ryukyu chain includes the most famous island is Okinawa, but this is a bit further north. It's close to an island known as Amami Oshima, but it's to the east of there. So the reason I'm here, of course, is because it's an interesting place for studying paleo sea level change. So Kikai Jima is a island with a rim of coral reefs around it, but also the island is uplifting, so it preserves corals from a lot of the time period between 120,000 years ago and present. They've published a book on the different kinds of corals that you find in this region, and it's all in Japanese, but there's a lot of different corals, and I'm only really just starting to know how to identify the different species, but hopefully this book will help. So I'm recording this on July 31st, and the first episode I recorded in June, and you're probably going to be listening to this in much later than that. But so some of this information is probably going to be a bit dated, but I think it's still interesting. So first off, the reason why it's taken a bit of time to get the podcast started is because I'm doing a lot of traveling. So at the end of June, I went back to Canada, where I'm from originally. And the reason I went to Canada was for a family event, but I also was invited to go to University at Buffalo. And I was invited by Jason Briner, who's a really well-known geologist who studies the Greenland ice sheet. And he invited me to go and visit because he was interested in what I do, which is, of course, modeling ice sheets in the past, as well as studying sea level changes. So he wanted to use the model of creating ice sheets that I wrote and use it in an educational context. So I will publish something to do with that pretty soon, and maybe even by the time this podcast comes out. The other person I met was Sophie Nowicki, who is involved in the ice sheet model intercomparison project. And what the ice sheet model comparison project is, they use a bunch of different models to try and figure out what the evolution of the Greenland and Antarctic ice sheets will be in the next 100 years or so, because they're, of course, interested on what that would contribute to sea level rise. This has a big society level importance. But these models are not necessarily telling you the same thing, because a lot of the physics behind ice sheet flow is not very well constrained, and there's also processes that are missing in a lot of ice sheet models. So Sophie was interested in asking me about how to sort out the glacial isostatic adjustment, which is to say how the Earth's surface will change due to the change in the loading of the ice on the surface. And in the past 10 years or so, it has become very clear that this is an important feature to determine how quickly glaciers will retreat in a marine environment. So basically, if the ice retreats, then the land will come up, and because of that, the amount of warm ocean water that will get underneath the place where the ice is touching the ground might be decreased, and that might reduce the amount of retreat of the glaciers compared to what you would expect if that wasn't the case. So we'll see how that goes. That will be in the next ice sheet model intercomparison project, and maybe I'll get involved if I have time. So the next thing I will talk about is that it's super hot. So the past week in Japan, it has been very, very hot, and in some places it's been exceeding 40 degrees Celsius, and that's approaching the hottest it's ever been in Japan. And where I live in Kumamoto, there were a couple of days last week where it was almost 40 degrees, and that's quite unbearable. In Kikai, we're surrounded by the ocean, so the temperatures are not quite as hot, but it is still quite hot, like mid-30s or so. And I've been making some videos that will be in a future podcast episode, and you'll see me very much covered in sweat while I'm doing these videos. So I hope people don't mind that. But I was also very covered in sweat, and I had to cool down before I started recording this. Yeah, it is very hot. And of course, Japan is not the only place that is hot. So according to the Copernicus Climate Change Service, which provides daily reports on global temperature, they expect that the hottest global average temperature that has ever been recorded happened last week. It might have happened for a couple of days. Of course, that's only exceeding the record highs that happened last year. So last year was there's a weather phenomenon called El Nino, and that generally will cause the global average temperature to be warmer because a lot of heat is coming out of the Central Pacific close to South America. So it's releasing heat out of the ocean, and that will cause the global average temperature to be higher. But of course, this is still much warmer than previous El Nino periods, and right now we're sort of coming out of the El Nino period and should be entering a La Nina by the end of this year. And if we think about that, we should be starting to cool down from that El Nino high temperature, but that hasn't happened yet, and that is something that scientists are a bit unsure of why the temperatures are so much higher than in previous years. So even compared to the El Nino La Nina transition just a few years ago in, I think it was 2016, it's still far warmer than what was before. And NASA also confirmed that this is definitely the hottest we've ever experienced, at least in recorded history. And on top of that, we're also seeing that the anomaly for sea ice area is also at a record low. It's not the absolute record low because usually that will happen in September when the Arctic ice cap reaches, or the Arctic ice, sea ice reaches its minimum extent. But if you sum Antarctica ice and Arctic ice, right now it's at a record low for this time of year. And this is being driven by an extreme heat wave in the India Ocean sector of the around Antarctica. And of course, the global temperatures being at a maximum and the sea ice being at a minimum, those two things are probably connected. It's maybe a chicken or egg situation where maybe the sea ice being low causes the warmer temperatures, but maybe the warmer temperatures cause the sea ice to be not growing as quickly as it normally does. You know, it's maybe a feedback loop. So that's sort of how things go, though. There's these feedback loops that if you change the system in one way, it will accelerate changes and make sort of like a catastrophic failure of the sea ice. Maybe we'll see how things go in the next couple of decades. So we'll see, because it wasn't that long ago that the Antarctic sea ice area reached an all-time maximum, according at least as far as the satellite records go back, which is into the 1970s. So it reached an all-time maximum, and now it's shrinking. So we'll see how that goes. The root cause of this extreme heating of the world in the past year, it's really something that's baffled scientists, because it was exceeding the record by a large margin. And one of the things that some scientists thought might be driving this is the Hunga Tonga eruption that happened in 2022. So you probably remember that there was this massive undersea volcanic eruption, and it caused this big sound wave to go around the world a few times, and there were tsunamis all throughout the Pacific. This, because it was a volcano that erupted underwater, a lot of water shot up into the stratosphere. And if you put water vapor into the stratosphere, that will cause a net warming on the Earth, because it acts as a greenhouse gas. So there was a study that just came out by Schubel et al. And they basically went through all the data that would be related to the atmospheric impacts of the Hunga Tonga eruption, which includes that water vapor getting into the stratosphere, but also things like changes to the ozone layer, and also aerosols, which is the particulate matter that comes out of the volcano. So when they summed all of these things together, what they found is that the net effect of that volcanic eruption was that it actually would have slightly cooled the Earth. But, it's a volcanic eruption, so it's kind of a transient event. So by the end of 2023, they say, well, the effects from this eruption have already passed. So this is not causing the extreme warming that has been observed. And so we're going to have to think of something else. Like it seems almost like it could be a step change. Of course, we're going to need to measure the temperatures for the next few years to see, but when we're thinking in the context of the goal to keep global temperatures to being within 1.5 degrees of the pre-industrial average, we're already almost there. And of course, temperatures will go down during the La Nina. That will probably happen by the end of this year, but it's looking more and more likely that within the next decade or so, the global temperatures will exceed that 1.5 degree threshold. The next component of that is Jasper et al. Recently put out a paper to put the 2023 extreme warming event in the context of the past 2,000 years. And they used two climate reconstructions. One is from instrumental records from the Berkeley Earth data set, which goes back to 1850. And that's a time when we started to have enough weather stations around the world to be able to estimate what the global average temperature was. And Epsiode also used records from tree rings. So every year a tree will grow a ring, and depending on what the climate is, the width of that ring will change. So based on how wide these rings are, you can estimate what the temperatures were in the past. And of course, since trees really, especially in temperate climates, the trees only grow during the summertime, so it's a summer temperature proxy. And based on their reconstruction from the tree ring data, the temperature in 2023, the summer temperature, exceeded the range of natural variability that was estimated for the past 2,000 years. So basically, there's a range of possible temperatures because, of course, there's El Nino and La Nina cycles, as well as volcanic eruptions. So basically, in a stable climate, there's basically a range you would expect the summer temperatures to be in a global average. And basically, the 2003 summer temperatures were approximately 0.5 degrees above that range. So it really demonstrates how extreme the climate has become compared to the background variations. And of course, I'm from Canada, and we have this problem with the summer temperatures getting really hot. And in Canada, the past 2 years, there's been lots of forest fires. And there was a major forest fire in the town of Jasper in Alberta. And 1/3 of the town was razed by that fire, and the fire continues to burn and probably will continue to burn in that region for the foreseeable future, mainly because it's in the mountains and there's not really any way to extinguish it. And I went to Jasper just before I started my PhD, which was in Australia. And the reason I went there is my cousin lived in Jasper, so that's one reason. But another reason is there's this highway which is known as the Glacier Parkway, and if you drive along the Glacier Parkway, which is between Lake Louise and Jasper, you'll see so many glaciers. It's really amazing. And of course, the most famous of the glaciers there is the Athabasca Glacier. And this glacier is very well studied, and it is the source of the water for the Athabasca River, which flows northwards through Alberta. And it's been well studied, and what's interesting is that the tourist center is built on the moraine that formed at the maximum extent of the Little Ice Age, which was in the mid-1850s, I believe. And ever since then, the Athabasca Glacier has been retreating and melting away. And the retreat has been continuing, of course, and they've found tree fossils underneath the ice, and they've radiocarbon dated that, and those dates go to the mid-Holocene when the global temperatures were sort of at a maximum. So that tells you that the Athabasca Glacier is already at sort of its minimum extent since the deglaciation happened. And it's continuing to retreat, of course. And you can visually see the retreat based on where the margin of the ice is, but also you can see it in terms of the thickness change. And as you retreat the margin, it's also changing, like the volume decrease has been quite substantial. So Jasper, in terms of it's being impacted by the fire, it's really terrible. And going along the Glacier Parkway, you can also very visually see the impacts of the warming that has happened in the past 170 years. So that is it for the introduction to this episode. Okay, and now on to the main topic of episode 2 of the Raised Beaches podcast. So last week, I explained what raised beaches were and how it related to sea level. Now, I think it's time to take a step back and say, what is sea level? And at Kikai Jima, I will be discussing in a future episode about how to measure past sea level. And there are several concepts that go into that. But yeah, first you need to know what sea level is. So sea level is a surface where the geopotential is equal. Now, I'll explain what this is. What is a geopotential? So when we talk about a potential, we're talking about energy. So potential energy is basically what happens if you have an object that a force is being exerted on, and if left to its own devices, that force would act on the object, and that is called potential energy. So like if you're holding an object, like let's say this, I'm holding it up in the air, and the force of gravity is pulling down on this. So there's a potential amount of energy that would be released if I let this go. And that is what we talk about when we say potential. And the geopotential is the potential due to two forces. So, of course, talk about gravity. The mass of the Earth causes things to fall down. But there's a second force that is acting on things at the surface of the Earth, and that's the rotation of the Earth. So basically there's a centripetal force, and that's pushing things towards the center of the rotation of the Earth. And that reaches a maximum at the equator, which is the furthest away from the axis of rotation. So at the equator, the centripetal force is at a maximum. And this actually causes the Earth to deviate from being a sphere. So basically, in order to keep the geopotential surface of the Earth itself from deviating from this constant value, it actually causes the shape of the Earth to be what's known as an ellipsoid. So the Earth is, generally speaking, when you're doing measurements of elevation, it's usually against this theoretical surface known as the ellipsoid. And anyway, the sea level surface is not the same as the ellipsoid, and that's because the force of gravity is not constant around the world. So basically, because the Earth is not uniform, like there are mountains and there are, oceans, and there's, stuff in the center of the Earth. It's not, the same. It's not uniform all the way around the world. So force of gravity actually changes depending on where you are. And basically this deviation from this theoretical ellipsoid and what the actual geopotential surface that is the same is known as the geoid. The geoid, if there were no continents or anything, if there was just ocean on the surface of the Earth, the ocean surface would conform to this geoid. So this is measured using satellites that can measure the gravitation on the Earth. The difference between the highest place on this geoid surface and the lowest place compared to the ellipsoid, that there's about 100 meters in either direction. So places where the gravity is relatively high, the surface is higher, and places where the gravity is relatively low, the surface is lower. And in the place that's really the lowest is in the Indian Ocean, south of India, and the highest place is actually just north of Indonesia. So basically, in those places, compared to the theoretical shape of the Earth, if it was a pure ellipsoid, those two places are the places where the sea level height is most divergent from that surface. So basically, the Earth is like a lumpy potato in its shape, based on this idea of the geopotential. So yeah, basically, because of that, when you have rain falling down on the continents, that water wants to be pulled towards the ocean because it will be above the geopotential surface, the geoid. So all water wants to go to the ocean. Of course, it can be stopped. It can freeze and form glaciers, or it can get locked into the ground as groundwater, or it can be in lakes. But eventually that water wants to go to the ocean because it wants to be on that surface of equal geopotential. The next step in what I want to talk about, so in future episodes, I will be discussing past sea level changes, and there are a number of things that cause geological features, geological proxies that indicate past sea level position that are not related to sea level. So if you're deducing past sea level, you have to think about these deviations from the sea level. So first, of course, are tides, and what we think of sea level, and it's the tides are averaged out. So the tides are caused by the gravitational attraction of the moon and the sun. So basically, the moon is going around the world, and the moon is exerting a force as well. So it's exerting a force in addition to the gravitational attraction of the Earth and the centripetal forces of the Earth. And because of that, in the surface of the ocean will go up and down based on where the moon is. And it's not the exact same position as where the moon is, because there's kind of a lag because of basically frictional forces. So basically the water surface will lag where the moon is. And depending on where you are, you can have tides as high as, in some places, it's up to 10 meters. So the water surface will go up and down a whole lot. And The height of the tide is dependent on the geometry of the seafloor where you're having the tide. So if you have a relatively shallow area and maybe an inlet, the tides will be higher because the water is being focused in there. So when we talk about sea level, the tides are the tidal levels are removed, so it's basically averaged out. The next thing that you have to be aware of is the effects of weather. So if there's a big storm like a typhoon or a hurricane, this will cause a surge in the water towards into the coastal areas, and the amount of that surge will depend on the severity of the storms. So basically, it's mostly due to the wind pushing the water towards the coast, but there's also a small effect because of the low pressure in the storm itself will cause the water level to rise because it'll decrease the geopotential surface temporarily. So if you're interpreting a paleo sea level indicator of past sea level, you have to beware that some of these features are affected by storms. Another thing you have to be aware of are tsunamis. So tsunamis are caused by earthquakes or submarine landslides, or even in some cases like ice falling into a fjord. So we're all familiar with the major tsunamis that happened in Tohoku, Japan in 2011 and in Sumatra in 2003. And those were caused by subduction thrust earthquakes. So basically, the ocean plate is descending below the continent, and at some point it just went and that caused a displacement of the water column. And because of how broad of an area that happened, it creates a massive wave, and that is very devastating. It can also be caused by landslides. So in Kumamoto, where I live, in the 1700s, there was a landslide caused by a volcano collapsing into the bay, and there was a 30-meter tsunami there, which was very devastating. And the largest known tsunami was caused by the collapse of a glacier in Alaska, which was upwards of 500 meters high, and luckily nobody was living there at the time. So if you're interpreting paleo sea level indicators, you have to be aware that some of these deposits could be created by a tsunami and not related to actual sea level changes. So this is something we have to keep in mind. So another thing you have to be aware of is that sea level can change due to shifts in ocean currents. And here in Japan, this is measurable. So there's this so-called western boundary current, so known as the Kuroshio. So basically, the water in the tropics will hit the continents, and it's directed northwards and goes along the western side of the ocean. The Kuroshio current brings warm water from the tropics towards Japan, and then it curves eastward, north of Japan. But this current, it shifts, and it shifts because of the geometry of the ocean bottom and other factors, which I won't go into. But the main result is that sometimes the current bends far southwards, and that will change the sea level by a few, like upwards of 15 centimeters, and this is measurable, and this is not the only place this happens. So, but this is a temporary effect. Like basically because the ocean currents are bringing warmer water or cooler water. It will cause the local sea level to drop depending on where the ocean current is. This is something that you can see in some paleo records. Like I read a paper that I'll talk about later, where they measured the shifts in the major ocean current in the Pacific Ocean, and it represented changes in the El Nino La Nina oscillation, and over time there's long-term changes to it, which they found by recording the paleo sea level changes using corals. So it was very interesting. The last thing I'll talk about on this topic of things you have to think about when you're interpreting past sea level is changes to ocean salinity and temperature. So a large proportion of the recent sea level change, which has been going on for the past 35 years or so, has been a result of changes in ocean temperature. So what's happening is, as you raise the ocean temperature, that causes the density of the water to decrease. So, what happens when you do that? That causes the water to expand. So, in some places where the water temperature has been warming up a lot, that is significant. So, in the order of tens of centimeters in some places. However, in the long term, this is not something that you can really deduce from paleo records, unless you have some really good climate reconstructions to go along with that. So it's something we have to think about, especially when we're thinking of glacial times. So during glacial times, the ocean water was a lot colder than it is now. So that would have had a small effect on what global sea level would have been at that time. But it's really hard to quantify. We don't really. It's not significant compared to other things, which I will discuss in a future episode. In the upcoming episodes, I'm going to talk about things that impact sea level on longer time scales and that are much more important in terms of paleo records, which includes tectonics and interglacial cycles. Like glacials, the buildup of ice on the land is what really drives most sea level changes on time scales of tens to hundreds of thousands of years. So those will be in upcoming episodes. So I hope you will tune in. Thank you. Well, now that we've discussed about sea level, I thought I would give some commentary on today's topic. So if you're watching the video of this, it should be pretty clear that I'm no longer in Kikai. And in fact, I'm recording this about 2 months after that. So in Kikai, I was teaching at a summer school for middle school and high school students, and basically introducing them to science. And my topic was on sea level changes, of course. And Kikai, of course, is an interesting place because it's a rapidly uplifting island. So I showed them not only the paleo sea level that can be deduced from these uplifted coral reef terraces and the coral fossils, but I also went diving into the water. And in those places, you can find these so-called micro atolls, which I will discuss in a little bit, that give evidence of recent sea level rise in Kikai. So Kikai is still uplifting. So the fact that there's evidence of sea level rise, it shows that the global sea level rise is probably going faster than the uplift rate. And yeah, it was a lot of fun, and I think the students really enjoyed it. And they invited me on their line group, and they were talking about their experience at the summer school for several weeks after it was already over. And yeah, since two months have passed, there's been a couple of things that have come up. One I'll discuss right now and the other thing I will discuss in the next part of the podcast episode. The first was that there was a new book called Sea Level: A History by Wilco Graf von Hardenberg. And this book, which I have not got this book yet, but von Hardenberg wanted to discuss the history of sea level in terms of both the geophysical measurement as well as why people wanted to measure it. And there is an article in the New Yorker that sort of gives an overview of this book. And anyway, it sounds very interesting, and I hope to pick it up. One of the stories that is mentioned in this New Yorker article is the story of the so-called the Seals Rock in central Sweden. And the story behind this rock is that there was this fishing village in central Sweden, and there was this rock that the seals liked to sit on. And the fishermen noted that it was getting to the point where the seals were no longer able to get to these rocks. And decades later, so this was back in the 1500s, decades later, the scientist Anders Celsius of the temperature scale fame went back and tried to find this rock, and he noted that the rock was now sticking out of the water quite substantially. And he estimated that there must have been a relative sea level fall to explain this change in the elevation of the rock versus what sea level was. And it was one of the first very conclusive pieces of evidence that sea level can change through time. And anyway, at the present day, because this area is uplifting about 1 centimeter a year due to glacial isostatic adjustment processes, this rock is now located in a forest. So it's a very interesting spot. I didn't get an opportunity to go to see this rock when I lived in Sweden, but hopefully someday I'll be able to get there. Another thing that I wanted to mention is that how we measure sea level. So, of course, we can have tide gauges, which are located in settlements around the world, but this only gives you a very narrow picture of what sea level is in areas along the coast. So back in the late 1980s, they decided, well, we can measure the sea surface height using satellites, using a technique called satellite altimetry. So what this is they launch this satellite, and it has a radar on it. So the satellite shoots a radar beam down towards the surface. That radar, a signal, reflects off the surface of the ocean, and then it comes back to the satellite. So what it does is it measures the time it takes for that signal to bounce back to the satellite. And based on how long that takes, you can estimate the sea surface height to a very high precision, like within a few centimeters. And these satellites have been orbiting the Earth since the early 90s, and has given a clear picture of the regional changes in sea level. And we can estimate the global average sea level rise at a much higher precision than what could have been done before with just coastal tide gauges. And one interesting anecdote when I was doing my PhD is that the second of these satellites, the Jason-1 satellite, when they compared the measurements with the first satellite, which was called Topex Poseidon, they noted there was a constant offset in the sea surface elevations that they were measuring with this new satellite. And they were scratching their head for some time to figure out, why is there this offset? Like, it doesn't make any sense. And eventually somebody realized that that offset was exactly the distance between the where the radar signal shoots off from and the receiver on the satellite. And that offset was basically this distance, and it really showed how accurate the altimeter was that this small offset of just a few centimeters was detectable through neglecting this distance. And so that was a very interesting anecdote from my time during my PhD. Finally, I thought I would discuss a bit about tsunamis. So I did my undergraduate degree in geophysics, and one of the courses I had to take was on earthquakes. And of course, we studied about, how earthquakes happen and how to measure them and the impacts of the earthquakes on civilization. But there was not so much discussion on tsunamis. And in 2004, when the Sumatra tsunami happened, I was sort of in the middle of my last year of my undergraduate degree, and seeing those images of the wave coming through and wiping out entire towns, and it really was quite shocking to me, and made me feel like being in geoscience was good, because I could be able to contribute to our understanding of the risks involved with nature. And of course, I'm doing this now in terms of sea level changes, but at that time I thought, well, maybe I should go into earthquakes, but it didn't happen that way. So in 2005, when I went to the University of Victoria, I was at the Geological Survey of Canada, and there was a lot of research there to figure out the hazards from tsunamis along the west coast. And of course, they figured out when the last major earthquake and tsunami happened in the west coast of Canada, and that happened on January 26, 1700. And they also know that it happened in the evening. And the reason they know that is because there was a tsunami in Japan, and they were able to calculate based on when that tsunami happened, when this earthquake happened. And of course, that tsunami was also devastating, and the folklore from the local indigenous people said that it wiped out entire towns. And of course, if that happened now, it would be very devastating, and it's something we all should be aware of. And when I was at the University of Victoria, they were creating this early warning system, so that if a big earthquake happens, there would be at least a few tens of minutes to prepare, so that people can get to higher ground. And lastly, I live in Kumamoto, which is in southern Japan. And, the 2011 tsunami that happened in Japan was a massive, devastating disaster, but it was not the deadliest tsunami in the history of Japan. And that actually goes to in the 1700s, there was a landslide that came off of the Mount Unzen volcano, and that landslide went into the Ariake Sea, which is right adjacent to Kumamoto City. And because of the shape of the sea, and also the proximity to Kumamoto City, there was a tsunami that was upwards of 30 meters high, and probably that devastated the city. And as far as I know, there isn't really much written history about that, possibly because and nobody was around everybody was busy trying to recover from that. In the hills south of the city, there's apparently some markers that showed what the elevation of that tsunami was. So, when thinking about the paleo sea level records, there are these tsunami deposits that you find, and they can happen in unexpected places, like in Kumamoto, where it's not on the side of the Pacific where you would find regular tsunami deposits due to megathrust earthquakes. But this was caused by a landslide, so it was a freak event. And these submarine landslides, or even landslides from mountains or whatever, this does leave a record in the geological record. In terms of paleo sea level research that I've done recently, there's the Stortega submarine landslide off the coast of Norway, which happened about 8,000 years ago, and that caused a tsunami that affected northwestern Europe, and you find evidence of that tsunami in places like Scotland. So it's not really a place you would obviously expect to see tsunami deposits, but it can happen. And trying to predict when a tsunami of that kind can happen is probably impossible, but it can happen. So there's not much we can do about that, but except survey the bottom of the ocean and see where it could happen. And anyway, in the next topic, I will discuss one of these kind of tsunamis that were maybe a freak event, and you will. It was a big news story last month. All right. In this episode, I'm going to discuss two papers, and these are both related to things that I talked about in the main topic today. The first is a paper by Yan et al., and it's entitled Significant Sea Level Fluctuations in the Western Tropical Pacific During the Mid-Holocene. And this was published in the May 2024 issue of Paleoceanography and Paleoclimatology. So in this paper, they were investigating the past sea level changes in the South China Sea, specifically on Hainan Island. And they were interested in the Holocene sea level changes. So that includes a period that covers the past 7,000 years. And they used a proxy known as a microatoll. And first, I mentioned microatolls before. And what is a microatoll? And what this is, it's a type of growth of a coral. So there's certain types of corals that grow in mounds. And one example is a species of corals known as Poroides. And what happens is Poroides will grow in a mound and it will expand outwards and until it reaches the low tide level. So the corals cannot have to live underwater, so they cannot really survive a long time if they're exposed to the air. So if coral grows up to the low tide level, basically it can no longer grow upwards. So these types of corals will only grow laterally after that, and you'll basically get a flat surface on top if sea level is constant. However, if sea level changes, then the corals will have to accommodate that sea level change. If sea level rises, you'll start to get a rim around the edge of the corals because the coral can then start to grow upwards again. And if sea level drops, then you get a sort of a staircase on the side of the coral. And as a result of this, microatolls are very precise way to measure past sea level because this where the coral can grow is intimately related to the low tide level. So in the study by Yan et al., they sampled 9 microatolls, and these microatolls are currently exposed during low tide levels. So it's an indication that in the past sea level was higher than present. And from these 9 corals, they all record at least a couple of different time periods of different sea levels. So what they did is they sampled the corals and then did precise uranium-thorium dating. And that allowed them to figure out when these corals were growing. And because of the fact that they're microatolls, they can pinpoint what the past sea level position relative to present at a very high resolution. So these 9 microatolls that they measured grew between 4,000 and 6,500 years ago. And one thing that's noted is that the paleo sea level sort of, on the whole, shows a general lowering of relative sea level by about 80 centimeters during this period of time. And they didn't explicitly say this, but this is probably an effect of this ocean siphoning effect that I mentioned in episode 1. So, but on top of this, this general decline in sea level, there were fluctuations on the order of 50 centimeters of sea level changes detected in these microatoll records. And yeah, of course they want to figure out why are these major fluctuations, and because these are microatolls, these are probably very robust records of short-term sea level changes on the order of centuries. And their hypothesis is that this is related to the so-called Walker circulation. So Walker circulation is basically the air circulation pattern in the tropical Pacific region. And this comes about because of the difference in air pressure between the western and eastern sides of the Pacific. So it's driven by the fact that in Indonesia, in the Indonesia region, there's generally a low pressure system, while in the eastern Pacific, there's generally a high pressure system. And the difference in pressure is kind of maximized during La Nina events. And so during this period, the water circulation is quite strong. And because the wind along the surface of the ocean goes westward, that causes the ocean water to be pushed against Asia. And that can cause a sea level change on the order of tens of centimeters. And during an El Nino event, when the Eastern Pacific is much warmer, this high pressure system is not as strong. So basically, the water will go back towards the east, and it should cause a drop in sea level along the Asian coast. And what they presume is that when there were these excursions of relatively low sea level in this South China Sea record, that this was probably during a period when there was a dominant El Nino phase during the Holocene. So, like I said in the main topic, sea level changes can happen due to these sort of very short-term fluctuations in the climatic system. So one thing they noted is that some of the climate models have kind of predicted that the water circulation should weaken due to global warming, but thus far that hasn't been the case. So something that scientists are researching now. The second paper is by Svenevig et al., and it's entitled "A Rock Slide Generated Tsunami in a Greenland Fjord Rang Earth for 9 days." And this was published in the September 13th issue of Science. And what this was is that in September 2023, there was this unusual seismic signal that was recorded in seismometers all around the world. And it didn't look like an earthquake, but this persisted for several days, in fact 9 days. And because we can say where the signal was, they quickly identified that this had to have happened in eastern Greenland. And they tracked it down to this place called Dixon Fjord. And if you don't know what a fjord is, it's basically a very narrow channel along the coastal regions of places that are kind of mountainous. And the fjord is dug out due to erosion from glaciers. So what caused this earthquake signal? It was from a rock slide, and what happened was that this chunk of the mountain adjacent to the fjord collapsed, and it caused a landslide, and it basically went through this valley that had a glacier in it, and it hit the glacier and it broke part of that off, and it may have also caused a bit of a submarine landslide as well. And all this material going in this narrow fjord basically caused this earthquake signal to start. And yeah, there was pictures from before and after this landslide, and you can see just how much material was taken away from the landslide. So all that material going into the fjord caused a tsunami because the water gets displaced. I mentioned in the previous segment about how Mount Unzen collapsed and caused this major tsunami in Kumamoto, but because this fjord is so narrow and so deep, the size of the tsunami was much bigger, and in places there's evidence that the tsunami wave was upwards of 200 meters high. So this was, very luckily nobody was there, but of course, if people were in this fjord, a 200-meter wave coming at you would probably not be survivable. And the fjord is quite restricted, but even in the adjacent fjords, in some places they said the tsunami was upwards of 6 meters, and there was a research base where luckily nobody was there, but it's clear that tsunami wave went inland upwards of 80 meters and damaged the research base. So that's it was quite shocking, obviously. And this 9-day signal, what they think happened was because of the geometry of the fjord and the fact that the landslide went along the side of the fjord. It caused what is known as a seiche. So after the initial tsunami, basically the wave would bounce off one side of the fjord and then bounce back, and then it keeps doing that, and basically it goes up and down and up and down. And this is what a seiche is. When I was a kid, we replicated the same kind of thing in our swimming pool, where everybody would have these little paddles that you could float on, and you'd go up and down and create waves. And basically over time, the waves in the pool would start to cause the water to slosh out the sides of the pool. And the seiche, because the fjord is 500 meters deep and only a couple of kilometers wide, this sloshing, which happened every minute and a half or so, basically continued on for 9 days before it stopped being detectable in seismometers. Anyway, the main points they had is in the reason that this landslide happened is in part because the land is destabilizing, because things are warming up due to global warming, and this kind of landslides that happens in a glaciated area, it's not unique. And, I published a paper on Greenland sea level change, and yeah, there was a few years ago, there was a similar landslide-generated tsunami that did affect a town in western Greenland. And, they went back to the seismic records, and they found that in this Dixon Fjord, there were, 4 of these kind of landslides that happened before. Obviously not as big. And in fact, another one happened in October 2023. In places like this, it's a big hazard, of course. And, the local government was kind of upset that the scientists that were conducting the study didn't notify the government that this had happened, and that they found out about it on the news. And yeah, it's something like this should really be communicated. And I don't blame anybody for that, of course. Scientists are going to be excited about this, but there is a human dimension to our kind of research, and this is why I think it's important to do a podcast to sort of communicate why this happens. Yeah, tsunami hazards due to glaciers collapsing in water is a big hazard in glaciated areas. And, it's happened in Alaska. There was a 500-meter high tsunami in a fjord in Alaska. I think it was in the 1960s. And that was the largest known tsunami in at least the past 100 years or so. One of the things that they talked about is how the tsunami probably wiped out all the archaeological records. And as a paleo sea level researcher, paleo or archaeological records often make up the best records of best proxies of past sea level in the past few thousand years. And it is kind of sad when these things are destroyed, but we do have to understand that in places like this, the geological record, especially things near the surface, are not necessarily permanent. So I do hope that things like this do spur more thorough research along the coast of Greenland, and that we can preserve and record the archaeological sites, as well as the proxies for past sea level change. So that's it for episode 2 of the Raised Beaches podcast, and I hope you tune in next time. Thank you. Thank you for listening to the Raised Beaches podcast. If you enjoyed this, please follow my social media accounts, where I post more information on the paleoclimate sciences. I am on Mastodon with the username @DrEvanGowan@FetiScience.org. On Blue Sky, my username is @evangowan.bsky.social. On LinkedIn, my username is Evan James Gowan. I hope you tune in next time. Thank you.